Welcome back to our dynamic programming series. Today we are tackling LeetCode problem 42, which is called edit distance, which is another medium level challenge. If you're new to DP or need a refresher, I recommend checking out the first video in this series where we covered the basics. This is our fourth video, so let's dive right in. First, let's go through the description of the problem. So given the two strings, word1 and word2, return the minimum number of operations required to convert word1 to word2. You have the following three operations permitted on a word: insert a character, delete a character, replace a character. So let's see an example. So if we have word1 as horse, H-O-R-S-E, word 2 is Ross, R-O-S, the output should be 3. How? So we can first replace letter H with R. That will be the first operation. So this H with R, and the resulting word would be R-O-R-S-E. Then we will remove the middle R from here, and the result would be R-O-S-E, and then we will remove E from the end, and the result word would be R-O-S, which is the word equal to word 2, meaning that with these three operations we can transform horse to Ross, and in this case that would be an optimal solution. So we can't do it with less than 3 operations in this case. And let's quickly also go through the constraints. So both word1 and word2 have length between 0, including 0 and 500, meaning that even empty strings are permitted as input. And word1 and word2 consist of lowercase English letters. So let's see how we can implement this. As I said at the beginning, this is another problem that we are going to solve using the dynamic programming or DP approach. And we have to implement this method or function called minDistance, and that takes two strings as input, word1 and word2, and the result value will be an integer that represents the minimum number of operations, and operations are insert, delete or replace a letter required to transform this word1 into word 2. Okay, so how can we solve this problem? Let me write down here an example. So we had horse and the other one was ROS. So we need to transform this word1 to this word 2. So as always, when using the dynamic programming, there are two common approaches, top down or bottom up. In this particular case, we'll be using the bottom up approach, where we will define some smaller problems. We will solve them first, and we will solve bigger problems by reusing the results from the smaller problems, and that way we will gradually build up the solution. We will be using a table which is called DP. So let's see how we can define a subproblem. Well, we can define a subproblem as DP using a table DP or matrix DP, and DP of ij can denote the solution of the same problem, but when transforming first I word letters of the word 1 into the first j letters into word 2. So this is how we can define our sub-problem. So I'll write this down. So minimum number of operations to transform first I letters of word 1 to first J letters of word 2. So that will be a definition of our dynamic DP table for solving this problem. So what would be the final solution? So final solution will be dp of m n, where m is the length of the word 1 and n is the length of word 2. So that would be the n solution. dp of mn would be the solution. Let's look an example. So dp, for instance, of 2, 2. In this case, I is 2, j is 2 as well. So we are transforming first two letters. So a subword containing first two letters of word 1 to a subword that contains first two letters of word 2. So in this case, it would be HO to RO. And the solution in this case would be 1. Why 1? Well, we can use a single replace operation. So if you go back to here, so we do have a replace operation, the third operation. So we can either insert a character anywhere, delete a character anywhere, or you replace a character, so one character with another, and every operation is counted as a single operation, as one. Okay, so in this case it should be 1. How? By using replace to replace H with R. So by replacing H with R here, we will transform this HO to RO, which is equal to RO. That is our goal for dp of 2, 2. So now when we have the sub-problem definition ready, now let's see how we can use, let's say that we need to calculate dp of ij, but as we need a formula to calculate this by using solutions from smaller sub-problems. So let's say that we want to, for instance, dp of 3 in this case. So that should be first 3 letters of word 1 needs to be converted to first 3 letters of the word 2. So that would be HOR. So the last letter is R in that case, into ROS. Last letter is S. So each letter of horse is R, each letter of rose is S. So how can we solve this? Well, basically there are two main cases. First case is when word 1 of I is equal to word 2 of J. So is R equal to S? No, it's not. No, it's not. So another use case is when word of word 1 of I is not equal to word 2 of j. That's our case for dp33, but for dp22 that is the case. So here we are converting HO to RO, and ith letter O is equal to jth letter O in this case. And so when dp of I is equal, when word 1 of I is equal to word 2 of j, in that case dp of ij is simply equal to dp of I minus 1 j minus 1. Why is that the case? Well, we don't need to convert the last letter to last letter here because they're the same. We just need to, so the solution for the dp of ij in that case would be equal to number or minimum number of operations needed to transform a subword that ends in I minus 1 to a subword that ends in j minus 1. Whatever it takes to convert this h to this r is the solution to transform the whole ho to ro. So this is the formula. When word 1 of I is equal to word 2 of j, dp of ij is basically dp of I minus 1 j minus 1. But there is a slightly more complex use case when word of I is not equal to word 1 of I is not equal to word 2 of j. So this is the case here with dp33. We need to convert this HOR to ROS. Okay? And here R is not equal to S. Then we have three options basically. One option is to use the replace function or replace operation to replace R with S. So that's one. And on top of that we need to add whatever it takes to transform what's before in the word 1 to what's before in the word 2. So basically one option would be to use the replace operation. In that case that would be 1 plus dp of I minus 1 and j minus 1. So one option is that. So we can use replace, so we can transform what's before, and this should already be calculated because it's a smaller subproblem. dp of I minus 1 to dp of I minus j minus 1. So whatever it takes to transform this smaller word to this smaller words or subword, and because they are not equal, R and S, we need to use replace to replace this R with S. So that's one option. Another option is to use the insert operation. In that case, when transforming HOR to ROS, we need to see how much it takes to transform HOR to RO, and to on top of that, because we transform HOR to RO, but we need ROS, we need to call one extra insert to add S there. So it should be 1 plus dp of I and j minus 1. So whatever it takes to transform this whole word to what's before the second word, so HOR to RO, and this is defined with this value dp of I j minus 1, whatever it takes, and on top of that, so we will simply transform HOR to RO, and now we have RO, but we need ROS, and we need to call one insert S at the end to get to get the final word ROS. That's why the formula is 1 plus the dp of I j minus 1. And third option is to use delete. In that case, whatever it takes to transform HO to ROS, but we need first to delete this R. So one option is to call delete R, that's one, and we will have HO, and then to transform it to ROS, and then we have ROS. So we are transforming what's before, so we are first deleting R from HOR, and we have HO, which is dp of I minus 1 to dp to the second word. That's why it's dp of I j minus 1 plus 1 to delete the word. So 1 to delete plus dp of I minus 1 and j. So there are three options. So which one we need to take when word 1 of I is not equal to word 2 of j? Well, we're gonna take the minimum value of these three. So it will be the minimum value between this, and this, and that's the formula, and that's basically the solution of this whole problem. And finally, we need to start from something. So our dp of 0, 0 will be initialized as 0. Why? Because dp of 0, 0 is basically empty word to empty word, and it takes 0 operations to transform an empty word to empty word. And also dp of 0 j and also dp of I 0 can be calculated. So dp of 0, 1 will be 1. dp of 0, 2 will be 2, because we are just inserting one extra letter every time. So this is how we're going to initialize this dp matrix. So dp of 0 j would be equal to 1 plus dp of 0 j minus 1, and dp of I 0 would be 1 plus dp of I minus 1, 0. And that's how we're going to initialize the word. Because why is that the case? Because, for instance, in this case, dp of 0, so we are transforming nothing to R, or nothing, that's dp of 0 I 0 1, and it takes one operation. Then we are transforming nothing to RO. That takes what it takes to transform this, which is 1, plus to insert O, that's 2, and then 3 for nothing to ROS. It takes 3, so we are inserting extra S. And in a similar way, we are initializing dp of I 0. It will be 1, 2, 3, 4, depending on the number of depending on the length of the word 1. Okay, so let's write this down. By the way, I'm using, as always, Java programming language. So yeah, we can assume that these constraints are always true, but anyway, yeah, we can add a null check at the beginning. So if word 1 is null or word 2 is null, we can simply throw an illegal argument exception, provided null values, or we can return 0, whatever you think it's more suitable. Anyway, yeah, we can assume even that these two provided strings are never gonna be null. Now we need to initialize our DP structure, which will be an integer of integers, DP, which is equal to new integer of integers, and we can say that int m is word1 dot len and int n is word2 dot length. So it will be m and n, but it will be +1, and here +1. Why is that the case? Because we said that dp of ij represents the minimum number of operations needed to transform first I letters of the word 1 to first j letters of word 2. So we need an extra space here for the 0 use case. So because I goes from 1 to the length of the words, and we also need an extra space for the 0, for the empty string use case. That's why we need this extra +1 here. And we can say that dp of 0, 0 is equal to 0. And now we can initialize dp of I0 and dp of 0j. So we can do something like for int I equal to 0, while I actually it should be 1, while I is less than or equal than m, I++. So dp of I0, so to transform first I letters of the word 1 to an empty string, will be equal to dp of 0, of I minus 1, 0, +1. So if the first word is horse, so to transform horse to an empty string, we need to take 1, 2, 3, 4, 5. We need to use 5 delete operations to delete E, to delete S, to delete R, to delete O, to delete H. Those 5 operations would transform horse to an empty string. So it heavily depends on the length of the word when transforming a word into an empty string. Similarly, to transform an empty string to the second word, so we can say for int j equal to 1, while j is less than or equal to n, j++, and dp of 0 j would be equal to dp of 0 j minus 1 plus 1. And finally, now when we have initialized dp structure, let's solve the problem by using this formula here. So it would be for int I equals to 1, while I is less than or equals than m, I plus plus, and for int j equal to 1, while j is less than or equal than n, j plus plus. And here we have two cases. One case is when if word 1 dot character at I is equal to word 2 dot character at j. So that's the first case. This case, then dp of ij would be equal to dp of I minus 1 j minus 1, because when the last two letters, so when the last letter from word 1 is equal to the last letter of the word 2, I mean not last but eth to jth, so to transform this subword to this subword, it takes whatever it takes to transform their prefixes, because they are equal, so we don't need to replace anything or remove or to insert a new character, etc. But if they are not equal, there are three cases. So we can either replace the last letters of the two subwords, or we can delete last letter from word 1 and then transform it to the word 2, or transform the first subword to the second, to the prefix of the word 2, and use the insert operation to add the last letter from the second word. So those three cases. So we need to find the minimum out of these three cases. So we can say that int min is equal to math.min. So math is a helper class in Java. It's part of the standard Java that just takes two parameters and returns the smaller element. So it would be dp of I minus 1 j minus 1 and dp of I j minus 1. And so we need one more min. So first parameter would be this expression, and second parameter, so whatever is smaller, will be compared also with the third option, which is dp of I minus 1 and j. Okay, and therefore dp of I j would be equal to 1 plus whatever is smallest between these three values, so 1 plus min. And this is it. Now when we calculated the values in the dp matrix, what we only need to return the final result, which would be dp of m and n. So we need to return it, and that should be it. Let's try this solution out. So here, as always, I have created this solution within the solution class. So I need to initialize it. So solution equal to new solution, and let's say here string word 1 is equal to horse, string word 2 is equal to Ross. So the solution is result is solution dot min distance word 1 word 2. Let's see what happens. Oh, we have an string index out of bounds exception. Let's see, let's look for, let's see where the word 1 at I M, it should be M is the word 1 and is the 3. Okay, let me see. Oh, sorry. So yeah, so the problem here is that we want to denote the ith value of the word 1, but given that word 1 is indexed with character, so if we want the first letter from the word 1, it should be char at 0. That's why we need to use I minus 1 here and here j minus 1. That's a little mistake, so let's try this. Okay, so the solution is 3 in this case. Let's use a couple of more examples. Let's say that we want to transform an empty string to Ross. Oh, sorry. For instance, to something like this. The solution should be 4, right? It's 4. Why 4? Because we need 4 insert operations. Let's say an opposite example. So 4 letters to an empty string. In this case, it should be 4 as well. Yes, it is, because we need 4 delete operations. And let's say we have A to B. In this case, it should be 4 as well. So it could be 8 if we delete these 4 A's, and then we use 4 inserts to insert 4 B's. But given that we are allowed to use the replace operation, so that can be that number of operations can be reduced to 4 by simply calling 4 times replace operation. Replace A with B, A with B, A with B, and A with B. So if we call this, yeah, the result is 4. So this seems to be the correct and optimal solution. And let's quickly go through the time and space complexity. So the time complexity here would be equal to, let's see, so this check takes constant number of operations, so it's basically O of 1, these 2 statements as well. And here we are initializing the DP matrix. So here, to initialize the first column of the matrix, it takes m plus 1 or m iterations. So this is O of m, and here this is O of n to initialize the first row of the matrix. So we can say it's, for all of this I'll use the constant number of operations, so O of 1 plus O of n plus O of m, and plus here we have 2 for loops. We have a for loop, outer and inner for loops. First one takes m iterations, the second one takes n iterations. So basically this whole for loop would take m times n operations, and here we have this comparison and this statement here. So this is all constant number of time. Also to choose a minimum between the two provided values, it also takes constant amount of time operations, because you just need to compare their values to return the result. And here we have 2 times, we are calling minimum method 2 times, but still it's the constant amount of time. Having said that, this section here takes big O of m times n operations, and to return the result it's the constant amount of time plus big O of 1, and therefore this function here grows faster than other functions. These constant functions, they don't grow at all, and these 2 functions grow in linear, are basically linear functions, but this one grows faster than these 2. Therefore this one would, with large m and n, this function would basically drive the time complexity of the whole solution. So the time complexity of this solution is O of m times n, where m is the length of the first word and n is the length of the second word. Speaking of the space complexity, in this case we need to add an additional dp matrix which has m plus 1 and n plus 1 rows and n plus 1 columns. Therefore this is an additional space. It takes an additional space, and therefore the space complexity would be big O of m plus 1 times n plus 1, which is basically, we can treat it as big O of m times n, because m and n drives the space complexity of the most of this solution. Speaking of the space complexity, this can be improved, but I'm not going to do it here today. But you can see the previous video where we were solving another DP problem, where we showed also how we can improve the space complexity. So maybe you can use a similar approach here, and I'll let you do that solution with improved space complexity, because every time we are using values from the previously solved subproblems, we are not going further than 1 row behind or 1 column behind, and therefore this space complexity can probably be reduced to O of m or O of n, or whatever is smaller between these two, between m and n. So if m is roughly equal to n, we can say if m is big O of n, in that case the time complexity is n squared. The same applies for the space complexity. So that will be all for this video. I hope that you liked it, and I'll see you in the next video. Thank you.